Today, the topic of discussion is on basic concept of refrigeration and air conditioning, that is Module 2, Part 1, PEME 601B. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. In this chapter, we will discuss simple vapor compression refrigeration system, that is VCRS, vapor compression cycle on pH and TS diagram, cycles with subcooling and superheating, their effect of changes in evaporator pressure and condenser pressure on the performance of a simple VCRS, dry compression and wet compression of refrigerant, actual vapor compression cycle. Now, simple vapor compression refrigeration system. So, in this schematic diagram of a simple vapor compression refrigeration system that is shown in the figure, it consists of the following parts. Number 1, that is the compressor. Number 2, that is the condenser. Number 3, that is the throttling valve. And number 4, that is the evaporator. Now, this is the compressor. Compressor is the main heart of the system, heart of this vapor compression refrigeration system. And after that, that is the condenser. Okay, so that after condenser, that is the valve, that is the throttle valve, and this is the evaporator. And so this is the cyclic process. So the discharge, that means this is the discharge valve and this is the suction valve. The refrigerant is passing through this system, through this pipeline, and it is entering into the uh, condenser. After condenser, it is entering into the throttle valve, and after that, this is the entering into the evaporator, and again it is entering into the compression. So this is the cyclic process. So LPV, that is the low pressure valve, low pressure vapor. So the low pressure vapor zone, and this is the HPV, that is the high pressure vapor. So this is the high pressure vapor, high pressure. So when that is the discharging from the compressor, the pressure and temperature both will very high, and that high pressure, high temperature vapor entering into the condenser. So function of the condenser is to condense, that means releasing heat, and that will be converted into the liquid, and that is entering into that throttle valve. There is a sudden drop of pressure, and that refrigerant will convert it to low pressure vapor. So the low pressure vapor and as well as the mixture of low pressure liquid, that is entering into the evaporator. So evaporator, so it is the very low pressure and low temperature, the mixture of liquid and vapor. So evaporator is a space where we store our food. So from that space, it will absorb, the refrigerant will absorb the heat and convert it into the vapor, that is low pressure vapor. So again, low pressure vapor entering into the compressor for further compression. So this is a cyclic process. Now, already I mentioned and discussed the function of compressor, condenser, throttle valve, and as well as the evaporator. Again, I am just um, telling you briefly, the low pressure and temperature vapor refrigerant from the evaporator is drawn into the compressor through the suction valve. It is compressed to a high pressure and high temperature into the compressor. The high pressure and temperature vapor are discharged into the condenser through the delivery valve. Already I have mentioned in my previous slide. Similarly, the condenser as a cooler consists of the coil and pipe in which the high pressure and high temperature vapor refrigerant is cooled and condensed. The refrigerant, while passing through the condenser coil, give up its latent heat to the condensing medium. The condensing medium is normally air or water. So after condensation, that refrigerant is passing through the throttle valve. its function is to allow the liquid refrigerant under the higher pressure and temperature and to pass to a controlled rate after reducing its pressure and temperature. That means refrigerant by passing through a controlled rate under a narrow passage, and that is called the shuttle valve. Some of the liquid refrigerant evaporates. So when it is passing through a narrow passage, there is a sudden drop of pressure, and some of the refrigerant will be in the evaporative state. The enthalpy of the refrigerant remained unaltered in passing through the shuttle valve. Next one is evaporator. It consists of coil and pipe in which the liquid vapor refrigerant at low pressure and temperature is evaporated and converted into vapor refrigerant at low pressure and low temperature. During evaporation, the liquid vapor refrigerant absorbs its latent heat of evaporation from the medium which is to be cooled. So this is the process 1-2. Process 1-2, that is the isentropic compression, and if you see the diagram 1-2, that is the isentropic compression where the um, entropy is constant, Q equals to 0, and work done by in this compression system W12 equals to integration V dV, that is the negative work, and the heat rejected in the process 2-3. So this is 2-3 process, so heat will be rejected and the superheated vapor, high pressure superheated vapor, will be converted into, that is the in the liquid state, that is state point 3. So here the heat rejection, that is H2 minus H3, H2 minus H3, that is uh, Q heat rejection. In the process 3-4, the isentropic expansion, that is H3 equals to H4. So there is a sudden drop of pressure. So due to the sudden drop of pressure, some of the refrigerant will evaporate, and in this case the enthalpy is remain constant. So here the enthalpy, constant enthalpy can easily be, so that enthalpy can easily be calculated. That is HF4. This enthalpy at state point 4 is nothing but the x into H1 minus HF4. That is the enthalpy difference of state point 1 and state point 4. So dryness fraction equals to x equals to is nothing but x3 minus HF4. F stands for fluid, and H3 means here this H3, and HF4 that is this point, and H1 minus HF4. H1 is this minus HF4 is this. Okay. Now in this case, that is the process 4-1 is the constant pressure evaporation refrigerating effect or heat absorbed. So this is the refrigerating effect, that is H1 minus H4. So QA is nothing but H1 minus H4. So COP of cooling is nothing but heat absorbed by work done. That the heat absorbed is QA, work done equals to W12. So just by difference in enthalpy, and it is the ratio of the two difference of enthalpy. Similarly, COP of heat rejected by work done, QR by W12, H2 minus H3. So H2 minus H3 divided by H2 minus H1, H2 minus H1, H1. Okay. So if you see the diagram, so this is the process. PV, TS and HS, that is the property diagram. Now from this figure, yes, from this figure we have the vapor dry and saturated in the beginning of the compression and superheating of the end of the compression. So QA, that is the area. If you see the diagram, 1 4 1 4 6 6 5 and 1. So this is the 1 4 6 5 1, that is the refrigerating effect, and heat rejected is nothing but area 2 2 dash 2 2 dash 3 3 7 7 5 5 and 2, that is the QR. So work done is nothing but W equals to QR minus QA. So that is the difference of these two areas. Finally, this so area is nothing but 44-76764. So that is the 44-7764. 764. So this area. So this is nothing but the 304-3 from the diagram. It is clear that this is nothing but this area. Now, when vapors are dry and saturated at the end of the compression, as shown in this figure, the refrigerant, the work done is nothing but 12301, and heat at 2, that is minus heat at 1, that is H2 minus H1. That is the enthalpy difference. Refrigerating effect is nothing but the area 1465 equals to the heat at 1 minus heat at 4. So that is the area under C04-3 equals to area under 44-764. So work done is W is nothing but area 1237641. Okay. Now the dryness fraction, if you see the diagram, dryness fraction X, that means how much the steam is dry, how much the refrigerant is dry. So that is the X X1 is nothing but the SG2, this is SG2 minus SF1. So this is the SF1. So divided by SG1 minus SF1. So SG1 point is this, and this is the SG1 point, and SF1 point is SF1 point is this. The difference of these two entropy, you can easily calculate the value of X1. Similarly, enthalpy at state point 1. Enthalpy at state point 1 means this is the state point 1. Enthalpy at state point 1 is nothing but HF1. HF1 means that is the this point HF1 minus plus x into Hg1 minus HF1. So this is the formula is same. Similarly, the specific volume can be written in the same formula. So QA is nothing but H1 minus H4. So H1 minus H4, that is the QA. Okay. So H1 minus, so H3 equals to H4. So we can write H1 minus H4 is nothing but H1 minus H3. And W equals to H2 minus H1. So enthalpy should be nothing but COP, that is the coefficient of performance, that is the difference of the two enthalpy. So QA by W equals to QA, putting the value of QA H1 minus H3 and value of W H2 minus H1. So this is the vapor compression cycle TS diagram and pH diagram. So this is the TS diagram and this is the pH diagram. That is the temperature, entropy, and the um, pressure and enthalpy. Now the COP of the vapor compression cycle is lower than that of reverse Carnot cycle. Power per ton of refrigeration, that is nothing but 3.5167 by COP divided by ton of refrigeration. Now refrigerant mass flow rate, that is M equals to, that is the ton of refrigeration by QA, that is the heat. So finally that will be 3.5167 by H1 minus H4 kilojoule per second. That is the refrigerant mass flow rate. Now motor power is nothing but M into H2 minus H1 by into 1000 into kilowatt. Volume flow rate of the refrigerant, that is the 3.5167 into specific volume by H1 minus H4, where V1 is the specific volume of the refrigerant at the inlet of the compressor. So it is nothing but that is the cross sectional area into length into n n divided by 60 into nv, where d is the diameter of the compressor, L is the stroke length, R is the RPM, and n small is number of cylinder, and nv is the volume specific volumetric efficiency. So finally, that is equals to 1 plus C into 1 plus C minus C into P2 by P1 for 1 over N, where C is the clearance ratio. Now mass flow rate of the cooling medium in the condenser is this. use of TS and pH chart. So if you see that the TS diagram, so that is the temperature versus entropy diagram. So there are different zones at the right hand part, that is the superheated region, and this line is the saturated vapor line, and this is the saturated liquid line, and saturated vapor line and saturated liquid line intersect at a point. That point is called the critical point, and the right hand part is the superheated region, and the middle one is the mixture of the liquid and vapor, and this is the liquid region, and this is the subcooled region. Okay, so this is the evaporation process. So 4 to 1, that is the evaporation process, and when that is the 1 to 2, 2 to 3, 3 to 4, 4 to 1. So this is the cyclic process. And this is the pH diagram of Vapour compression cycle. If you see the diagram, the different lines, this is again, this is the 1 to 2, that is compression, that is this line is saturated vapor line, and this is the critical point, and this is the saturated liquid line, and that is the 1 to 2, that is the compression. After compression, that is refrigerant is entering into superheated region, and 2 to 3, that is the condensation. The refrigerant is passing through the evaporation zone and entering into the saturated liquid line, and 3 to 4, that is sudden drop of pressure, that is the state point 4, that is the mixture of liquid and vapor, and 4 to 1, that is the refrigerating effect, this QH, that is H1 minus H4, and again refrigerant is entering into the saturated vapor point. Now if you see the different lines, so this is the constant volume line in this diagram represented by this dashed line, constant volume line, constant temperature line. One line is big, another line is small line, and this is the constant entropy, that is dash dash dash, dash small dash dash. So these are the constant entropy line, and this line is, that is the constant volume line, and this is the constant temperature line. So this line is constant temperature line. Now in this case, the various processes are also shown in this figure. It is the most convenient chart for studying the behavior of a refrigerant. The vertical ordinates represents the pressure, and the horizontal ordinate represent the enthalpy. The saturated liquid line and the saturated vapor line merge into one another at the critical point. The space to the left of the saturated liquid line is the subcooled liquid region. The space between the liquid and vapor lines is called the wet region, and the space in the right to the saturated vapor line in the superheated vapor region. So this is the superheated vapor region, this is the wet vapor region, and this is the supercooled liquid region. Okay, so these are the different regions shown in the help of this diagram. Now again I am discussing this process 1 to 2, that is isentropic process. State 1 to state 1 represent the saturated vapor, state 2 superheated vapor, process 2 to 3, that is the condensation. State 2 represents the saturated vapor, and state 3 represents the saturated liquid, and the heat is rejected to the condensing medium. Process 3 to 4, that is the throttling process, the enthalpy of the saturated liquid at state 3 is equal to the enthalpy at state 4 or 1. So this is the enthalpy. This is due to the throttling process, the enthalpy remain constant. So enthalpy at state 3 equals to enthalpy at state 4. The process 4.1, that is the evaporation, heat is absorbed from the medium and refrigeration effect is produced. So that is for process 4.1, 4.2.1, that is the refrigeration process, and this is called refrigerating effect. The pH in this pH diagram that is shown. Mm, So an R12 vapor compression system is operating at a condenser temperature that is at 40 degrees centigrade and an evaporator temperature that is of minus 5 degrees centigrade. Calculate the Carnot COP and actual COP of the cycle. So from the pH diagram, we can write the value of R12, that is enthalpy H1, H2 and H3 equals to H4. So Carnot COP, that is T1 by T2 minus T1 we know. So putting the value of the temperature, we can easily calculate the Carnot COP. So actual COP, that is H1 minus H4, that is divided by H2 minus H1. So putting the value of the enthalpies, and we can easily calculate the actual COP of the refrigeration. Now another problem, that is an ammonia refrigerating machine has working temperature of 35 degrees centigrade in the condenser and minus 15 degrees centigrade in the evaporator. Calculate the COP for dry compression and wet compression. The data for ammonia is given in the given. See, these are the chart table. This is the temperature minus 15 and 35. So these are the specific volume at fluid and gas. Enthalpies are also given. Entropies are given. So this is the superheated vapor are also given. And that is in a superheated vapor, the temperature corresponding enthalpy and entropy are also given in this table. So by interpolation of method, so we have to calculate the value of the temperature, that is del T, so that is 27.1 degrees centigrade. So degree of superheat at discharge, that should be 50 plus 27.1, that is 77.1 degrees centigrade. Discharge temperature is nothing but 35 plus 77.1, and that is 112.1 degrees centigrade. Similarly, from this we have to calculate the value of enthalpy at state point 2, and the refrigerating effect is nothing but H1 minus H4, that is already mentioned from my previous slide, and that is the work done. W is nothing but H2 minus H1, and so in this way you have to calculate the COP. COP is nothing but QA by W. So and that is the H1, that is the X1, that is the dryness fraction, that is the H1, that is the enthalpy at state point 1, that is the specific volume at state point 1. With this formula we have to calculate can easily, and QA equals to H1 minus H4, that is the enthalpy difference. Similarly, W equals to H2 minus H1 and COP equals to, that is the this is, you can easily calculate the value of COP. Thank you very much.